Hi everyone, and welcome to lecture 24. Continuing our discussion on transistors, and I'm hoping to basically make sure that we have a few key concepts discussed very clearly and formally, and to a large degree, hopefully this will also serve as a little bit of review. And basically, I'd like to continue the discussion on small signal behavior now, and make sure that we are clear on the connection between DC and small signal. DC and small signal analysis and the connection between the two. And most of what we will discuss here is applicable to equally to MOSFETs of either type and BJTs. The general idea is that, well, first of all, when you're dealing with a circuit, at any point in time, if you look at a given node, there is a voltage there. Or if you look across any element, there is a voltage difference between every two nodes. And similarly, there is a current. Now, if you are doing a DC circuit, these voltages and currents are constant with time. Sometimes you encounter a situation, and this is very common, where you make small changes to these node voltages or in general voltages and currents in the circuit. And normally it starts from applying a small change somewhere, and that change then will propagate. And very often this takes the form of an AC signal. I think we talked about the example, for instance, of a small signal that an antenna picks up, and then you want to amplify it. And so that's a very common example. You build an amplifier that will pick up a voltage variation with time of, let's say, a microvolt, and then it amplifies it to tens of millivolts or even to volts. Very often that signal, again, has an AC form, a periodic form in time. It could be composed of multiple frequencies, and this goes beyond the topic of our discussion here. And you will be able to appreciate it in particular once you do signals and systems. But in principle, that change, the small signal variations that we talk about, does not have to be a periodic signal in time. It can just be a small change that you make and then stay there. Or then, stay there for some time and then make another small change and so on. Now, when you encounter a circuit that involves transistors, and let's say you're interested in DC operation, there's nothing other than writing your KVLs and KCLs, which could be done in the form of nodal or mesh analysis, and your element relationships, which for the transistors are a little more elaborate than what you had for resistors and capacitors and inductors. But the general approach is the same. And we've seen some examples of that. Now, if you wanted to now make a small change somewhere, you don't necessarily have to solve for the new values of everything. You can look into this small signal analysis. Or you do want to look for new values, but you can do it through this small signal analysis. And by that, we mean this. Let me just summarize what I just said. If we are concerned only with a DC situation, we just have to use the laws of circuits and element relationships. And you might say this is a general statement. This is not limited to only DC analysis. But if you have a situation where you have some small signal variations on top of a DC signal, you can break the problem into two problems and then apply these laws. So let me write that down. If we are concerned with small variations of the signals, meaning voltages and currents, around a DC bias point, we can break the problem down to analyzing the DC problem and then the small signal problem. The DC part would be called the large signal analysis, and then there's the small signal analysis. And again, like I said, the small signal can be in the form of an AC signal, but in general, it does not have to be. In practice, this is what we are talking about. For a given voltage, say the input voltage of the signal of the circuit, we have, this would be, let's say, the total input voltage, and I'm breaking it down into two components, the DC and the small signal. And of course, this also applies to any other voltage in the circuit or any current in the circuit. And again, none of this is specific to BJT or MOSFET. This is all general. The question is, what if the small signal is not AC? What could it be? By AC, we often imply a periodic change in time. Let's say you have a sinusoid with a given frequency, and you call that an AC signal. Whereas you could have a signal, a change that's not necessarily of that regular periodic nature. Let's say the circuit is sitting in some DC condition, and let's assume you have connected a power supply somewhere, right? Applied 3 volts, and the circuit, everything is working in DC, and the circuit is happily sitting there, right? And now you take the fine tuned knob of the power supply and change your 3 volts to 3.001 volt. Okay? There you have applied a small 1 millivolt signal on top of that 3 volt signal, right? And you've left it there. The response of the circuit to that 3.001 volt signal can be understood as its response to the 3 volt signal plus its response to the 0.01 volt signal, right? Even though that change is not AC in time, but it's small. It's still a small signal variation. Why is it that we emphasize this small signal? Why is it that I just gave an example? I said, if let's say I have a circuit with an input power supply at 3 volts, and now if I change the input by a small amount, let's say I increase it by 1 millivolt, I can find out the answer to the circuit as a sum of 2 different parts, the answer to the 3 volt and the answer to the 1 millivolt, right? That's what I'm saying by small signal analysis. Why is that? And why the emphasis on the small signal, even if it's not AC, like in this example that I gave, right? Now, to be sure, I can solve the circuit from scratch for an input of 3.001 volt. That's totally fine, right? But I'm saying I can also solve it as 2 separate responses, the response to the 3 volt stimulus and the response to the 1 millivolt stimulus. Why is it that I can make that change? Thinking back to what we talked about. That reminds me of superposition. I'm doing effectively superposition, right? I'm saying that I have an input somewhere in the circuit that I've called V in, like this, right? Small v, capital N. But I'm saying this I think of as the equivalent of this and this, right? This is what this statement here is saying, and what we said above that. And this is indeed superposition. I'm saying I can solve the circuit once, assuming this top voltage source doesn't exist. It's 0 volts. Solve for this. And then forget about this one. Solve for that. And then add the two. Now, there's a caveat. We have to be careful. When we solve for this in small signal, first we have to have the solution for the DC component. Because the small signal behavior or the change depends on where you started. That's one very important thing to keep in mind. But assuming that we follow that, we keep that in mind, then I can do this, right? But why is it that I'm emphasizing a small signal change? Why don't I just say, any change I can represent like this? Let's say I apply 3 volts to the circuit. I have a bias point of 3 volts. Now I change it to 5 volts. Can I break down now the solution of the circuit into the solution for the 3 volts plus the solution to the 2 volts on top of that? Can I do that? No? So is that superposition? Well, that is superposition. But is superposition applicable in transistor circuits? No. Why not? In a rigorous way, they are not linear components, right? They're not linear, and superposition is not applicable. The premise of small signal behavior is that if you make small changes, you can approximate the response of the transistor as a linear response. If you think about the characteristics of a BJT that have an exponential nature, well, if you are making a very small change to a voltage somewhere, you can approximate a section of your curve as a straight line. And that's what you're doing in small signal analysis. For the MOSFET, the characteristics are quadratic. Again, for small changes, you're approximating it with a straight line. That's what you mean by small signal. The question is, again, does it mean we are looking at a very short time? And the answer is no. It's not a matter of time. It's a matter of the change in the signal. If, let's say, this Vin was 3 volts, this little v, little n, was, say, a millivolt, depending on how much approximation you can tolerate, or a microvolt, then that's a small signal change. You become concerned about the time scale if you're really looking at AC analysis and time-dependent behavior. But this could be a quasi-static problem where you make a very slow change to this, but the amount of change itself is really what matters, not how fast you've done it, if you're, again, concerned with steady-state behavior. In general, you cannot apply superposition to BJT and MOSFET circuits because they're not linear elements. But if you're making very small changes, you approximate them as linear elements for the purpose of that change. And that's why you can look at the response to that small change on top of the response for the bias point. But again, note that there is an order in this. You first have to solve for the bias point. The change, the small signal response depends on the bias point. Let me just write that down to make sure we don't forget. Yes?
And what happens if capital E and capital N?
We have another question here, and this is, let's say, specific to the MOSFET. The question is this, and this is an interesting question. Let's say you're interested in the behavior of the MOSFET current, okay? We are looking at the total MOSFET current, the total signal, small I, big D, as a function of the total MOSFET VGS, right? Assume that you are in the saturation mode, and you have this quadratic behavior. If this is VT. Now, what the question is, well, if we were here, if this was my bias point, VGS, if I made any change around here to the voltage, it would correspond to this change on the current axis, right? And I am approximating this with a straight line. This is my approximate linear response, right? And of course, I've exaggerated things here so that we can see. That's the domain we are covering on the current axis with that. But what if my bias point was not there, but it was somewhere here, let's say, right? And now if I make a small change, one way I might go more into the on or saturation behavior, in this case. The other way, I might go below the threshold voltage into the off state of the MOSFET, right? How do I deal with this? And the answer for this is one has to be very careful. If the change, the small signal change that you apply, takes your transistor from one mode of operation, which is on and saturation in this case, to another mode, which is off, the equation for the transistor literally changes, right? The current goes from a quadratic behavior to 0, right? And therefore, you cannot describe this problem with just a small signal change. You can describe maybe the positive half of it with a small signal change, but not with the negative half. So it's a very important thing to keep in mind that when you apply small signal behavior, you have to make sure that the transistor stays within the mode of operation for which you are building your small signal model. Okay? That's why I'll cross this part out, so that note that this is not a correct way of analyzing something like that, because you're changing from the saturation to the off state of the transistor. From here, what I'd like to do a little more of is to look at the model for the transistor, both in DC and small signal. And in fact, we started the discussion of the transistor by looking at a model. Remember the first day we looked at a problem where there was a diode and a current-controlled current source, or a voltage-controlled current source for the BJT. I'd like to just kind of generalize that discussion a little bit. For the BJT, consider an NPN BJT. If you look at the collector current as a function of the base emitter voltage, what kind of behavior did we have? What was the equation for this? This VT being thermal voltage, this was an exponential behavior. And this is when the transistor is in the active mode. Which corresponds to this range on the VCE scale. Active. And this is the value of that current that's given by this equation. Okay? We've seen this before. And in that active mode, essentially we are saying to first degree, the current does not depend on VCE. It's just purely an exponential function of VBE. And therefore, if you wanted to model this device, you can think of it as this. Nothing new here. And this is your VBE measured like this. And this is your IC. Measured like that. This is where we started our discussion. Well, this is one of the DC models for a BJT transistor in the active mode. That's all it is. So this thing that I showed you at the very beginning, the circuit that we used as an introduction to transistors, is in fact how you would model a BJT in simple ways in the active mode. What if you wanted to make it a little more sophisticated, one step more sophisticated, and take into account the fact that even in the active mode, IC is not a flat line. That in reality, with an increase in VCE, IC changes a little bit, the effect known as the early effect. How can I augment this model to give me that physical reality, that that line is not exactly flat, but it's more like this, has a small slope? How could I make that happen in this model? What change should I make? Add a resistor. Because all that is saying is that the current IC is not only dependent on VBE, but also changes slightly with VCE. All I have to do is to add some resistor here to model the early effect. Now, does this, so if you look at this now, the total collector current is not this, but it's here. Maybe I need to connect this here. And this is my collector current. Okay. The total collector current is not only that exponential that depends only on VBE, but it's also the current going through that resistor, which depends on VCE. And now you might say there is a little bit of a trouble with that. Is this a good model? Does this accurately represent a situation where I have that current plus a current that only depends on VCE? Does anyone see any problem with this? Well, there will be a current through the resistor, but so that current, you're saying it doesn't depend on VCE. Or maybe I can be more specific. It does depend on VCE, surely. I mean, if things change in the circuit, that current will change. But not directly like that. It's really a direct function of VCB, right? Whereas what I wanted to model in the early effect was a dependence on VCE, right? An almost linear increase with VCE. So if I want to do that, then where should I connect that resistor? Instead of between C and B, maybe I should connect it between C and E. Is this now a good representation of what we want? A current, a collector current that's the sum. You see, this is what we want. We want a collector current that has that exponential part plus some VCE divided by RE, right? Is this model now good for representing this behavior? Is my collector current the sum of those two currents as drawn on the circuit? Well, here's the question. This is the collector current that I'm showing here. Is that IC, I sub big C, the sum of that exponential current plus the current through that resistor? Is it? So you're saying this is not good because the IC here is just that exponential current, right? So I'm getting into trouble here. So this is not good. Now you're making another suggestion. How about this? Can I do this? I will put it in parallel with this, right? because I want it to be added to that to give me the total IC. But looks like a resistor wasn't good in that regard, because the voltage I wanted was VCE. How about, this is, if I understand correctly, this is what you're saying. How about I say there is a current here whose value is VCE divided by some resistance, or basically some factor. You might even say alpha VCE. How about this? Is this good? Does this now give me an equation like this? That is that exponential plus something times VCE. Is this good now? Yeah, it's good. And what you just witnessed was the way someone would go about creating a model for an element, right? You reasoned your way through. And I think this is a very nice example, because you see how you start modeling nature. And you start with things that you know and with components that you have studied before, but you put them together in combinations that allow you to now represent a more sophisticated behavior, in this case showing the early effect. This works. This alpha is basically that slope of I versus VCE. Or you could think of it as a 1 over R type of thing, right? This alpha is of the dimension of conductance. It's the inverse of some resistance. Okay? So this does work. But this is not the most common way you see this done. I'll draw another way that this is done. Let me write it down. This does seem to work to represent the early effect, but it's not very common. A more common way is this. Here's a more common way. By the way, if I say something is not very common, maybe that's not a very good statement, because it depends. Maybe for a given application, you want to do something like that. So it's not a very, I don't like that kind of statement. It's not very well defined. But a more common way. If I want to go back to using a resistor to represent the early effect. Can you guys think of changing the model somehow to be able to do this with a resistor? Can I ask you guys to think about that for a couple of minutes? I'll change this alpha to some 1 over R, because it could be mistaken with the transistor alpha. So just change it to. Can you think of a way to have a model for the BJT that represents the DC behavior and also shows the early effect? Let's take a look at this together. And maybe don't worry too much about writing things down at this point, but just look here, because I want to point out something important. All I'm trying to do is to represent the device that has these IV characteristics with some known components. Current source, diode, resistor, such that they can capture the behavior in the active mode. And I want also to include that early effect, the fact that the current IC is not flat with VC in the active mode, but it slopes upward slightly. Now, to build a good model, let's first complete the previous model that we discussed. This here, let me just create a little more room. In this model, maybe I should be very specific about two other things. What is the base current in this model? I mean, I haven't said anything specifically about this diode and the base current, right? Remember, in the active mode of the transistor, the base current is just the collector current divided by beta, right? This is just the collector current divided by beta. And the emitter current is the collector current divided by alpha. Now, alpha was more or less 1, something like 0.99. So the emitter and collector currents are more or less the same thing. The base current is, let's say, 100 times smaller than that, just to be complete. Now I want to build a slightly different looking model, which is a more common way to also take into account the early model, or let's say, the early effect. How about this model? How about this? First of all, for now, neglect the early effect. Does this work for modeling the transistor in the active mode? You notice that the way I have placed the diode is different. Instead of putting it in the emitter branch, I've put it in the base branch. Can I do this? Is this a valid model? Can this represent the behavior, the IV characteristics of the transistor in the active mode? Neglecting the early effect for now. Yeah, because you see that your collector current has an exponential dependence on the base emitter voltage. No problem with that. And only depends on that. So is there a difference between this and this? Again, neglect the early effect part, but in the way that I have connected it. The only difference is these two diodes are not the same. This diode has the base current, right? The current in this one is IC over beta. And of course, the current here is IC over alpha, right? Whereas the previous model, the way I had included that diode had a current of IC over alpha. In that model, the diode was placed in the emitter branch. It had a higher current. It had to represent the emitter current. In this model, it's been placed in the base branch. It has a smaller current. It has to represent the base current. Okay? But this is an equally valid model. Now, what if I wanted to add the early effect to this? Can I use a resistor in this case? Now you see that this works, because now my total collector current is not this. This is just the exponential part. My total collector current is that. Plus VCE. Remember, this is collector, and this is emitter, and this is base, plus VCE over R. That's that collector current. Now this works. You see, this is just a different way of modeling it. A DC model for the BJT that also has the early effect. If you have a transistor in the active mode in a circuit and you want to solve the circuit, you can replace the transistor with this and solve it, as long as you know you're in the active mode. So we should say explicitly in the active mode. This is not something to memorize, but I want you guys to go through this exercise of how we thought about building this. and how we attempted first here. We had some glitch, and then we came up with another way to do it. And this is a very common way. Well, not this. Is this used over the previous one? The answer is very commonly this is used, but it really depends on the type of circuit that you're building. You will find one or the other more convenient depending on the circuitry around it. Okay? So there's nothing really too general about any of these things. Okay? And that's what I'm hoping that you guys will get out of it. I don't think there is any point trying to memorize one or two specific cases, but I want you to see how one goes about modeling a physical component. Okay? Which one is used really depends on which one you will find more convenient. But I'm also hoping that this shows that there are different ways of modeling these things. So if you see different transistor models, you shouldn't be afraid of that. And we won't have time to go through all of them. And again, this is kind of getting to the edge of the topic for this course. So just seeing one or two is enough. But next, what I'd like to do is to also build a small signal model for the BJT. So I'd like to ask you guys to think about what a small signal model for the BJT would look like. So think about this problem. Let's assume you have built a circuit like this. A circuit that we've seen before. Here you have the VCC. Here you have a collector resistor. Here you have another resistor. Here you have ground. And you have biased this with R1 and R2 here. And you're looking at this output voltage. If you assume that if you assume that the values of the parameters are such that this transistor ends up in the active mode, then you can replace the transistor with a circuit like this between base emitter and collector and solve the circuit. Okay. If you wanted a very accurate solution. And of course, very often, we've seen examples where we assume this VB is about 0.7 volts and we get an approximate solution, right? We've done that. Again, you don't necessarily do that all the time. Very often, an approximately constant VBE of 0.7 volts is good enough, and we've seen examples of that. Here's what I'd like to do next. What if I now add a small signal on top of this? And I'll do so by doing this. I have this circuit that biased the transistor. And I will add my input like this. A small input, a small signal input with a capacitor. Now this is what I briefly pointed out at the end of last time. And to make more sense of it, I ask you guys to think about an RC circuit. Now let's take a short break, and then we will talk about this a little more before discussing the small signal model. But in the meantime, if you want to also think about how this would help me add a time-dependent input signal. This is a discussion that, and we will talk about it specifically because we are interested in connecting this time-dependent, for instance, AC, small signal, V in, to that otherwise biased circuit. and then look at the variation of the output as a function or because of that small signal at the input. But the way I have coupled it with that capacitor, I hope is intriguing. And this is what I'd like to discuss a little bit. First of all, let's say you wanted to solve the DC behavior of the circuit. Think about the DC value of the collector current or the emitter current or the base emitter voltage and so on. What is the difference between the DC behavior of this circuit and the DC behavior of this circuit? What is the difference? Nothing. Because in DC, that capacitor is an open circuit. DC steady state. The capacitor does not let any current through because dV by dt is 0. There's no change with time. The DC behavior is the same. So basically, you can completely neglect the small signal source, and the capacitor, and solve for the DC bias point. But why is it then that I can use a capacitor like that to couple this small signal that is of an AC nature to the circuit? And for that, I ask you guys to think about this, or I asked you last time. And by the way, that is called a coupling capacitor. It allows me to couple that. But how does this work? For that, think of this. Consider this circuit. C and R. Let's call this some V in and this V out. In DC, there is no current going through. The capacitor is open. And V out does not see any effect of V in, right? In fact, in this particular circuit in DC, V out will be 0 regardless of V in. What if I make a sudden change to V in? What will happen to V out? Will it stay the same? Let's do a clicker question. Change suddenly. What does a capacitor not like to do? A capacitor does not like a sudden change in its voltage, right? That's something we've been saying in the past. Because why? The current is C dV by dt. A sudden change in the capacitor voltage, this is the voltage difference across the capacitor, will require an infinite current, right? Or a very large change in time, so a significant change over a short period of time will require an extremely high current that this circuit will have a cap on because the voltage will be only so much and the resistor will allow so much current maximum. A capacitor does not like a sudden change across its, or of voltage across its two nodes. Which means then, if you suddenly raise this, the other side will also rise suddenly. Now, this is all very qualitative, right? If I wanted to make it more quantitative, what quantity in the circuit tells me really how the V out, how rapidly it responds to V in? Let's put it another way. Imagine I change V in very suddenly, and we just argued, like we've said in the past, that then V out will have to change accordingly suddenly. But if I then wait enough time, what will eventually happen to V out? It will go back to 0, right? DC steady state, right? Because the capacitor will charge. What is the time constant that determines how fast V out will go back to its steady state? RC, right? The larger the time constant, the longer it will take for V out to go back to its DC steady state, right? In other words, the larger the time constant, the larger your RC, the more V out will stay close to V in when you change V in. Right? Let me repeat that. When I make a quick change in V in, V out will tend to follow quickly. But then if you give it time, it will settle back to 0. The capacitor will charge up, V out will go back to 0, the current will go to 0. But if the RC of the circuit is large, it will take a very long time for the capacitor to charge, right? For V out to go back to 0. It means for a longer time, V out will stay closer to V in, right? Or V out will kind of follow V in. Now imagine I keep changing V in back and forth, up and down. If I keep changing V in back and forth now, imagine this is V in with time. If I don't make just one sudden change, but I kind of change it like this, back and forth. I just argued that if your RC is large, this V out will kind of follow V in. If this is V in, your V out will be something like, maybe with some lag, maybe with some ratio, but it will tend to follow V in. This is what we are saying. You see, think of this as a series of maybe sudden changes. It will be more like this. Maybe this is easier to understand. V as a function of t. If this is my V in, sudden jump, then another sudden jump, another sudden jump. If this is V in, a sudden jump will lead to a sudden jump in V out. Then the RC time constant will want to make V out go down, or the RC behavior. But if RC is large, there won't be much decline in V out during this time. And then you have another jump here, and then another, and then another, and so on and so forth. So if RC is large, which means for a given R, if C is large, such that RC is large compared to the time scale of changes at the input, the output will follow the input more or less. This is the outcome. If RC is large compared to the time scale of the changes that you're making at the input, the output of that RC circuit will more or less approximately be similar to the input. I haven't drawn it accurately, of course, but you've seen this kind of circuit many times, so I don't want to dwell on that. Now go to this circuit. From this base node of the transistor, if you look to the right, there is some equivalent resistance there, right? Think of it as the Thevenin equivalent resistance that you see from that base. And there is the base current and the current in these resistors and so on. Think about that as some big R. Well, if this capacitor is large enough such that C times that equivalent resistance R is large compared to the time scale of variations of V in, the variations of V in will appear at the base node. That's exactly this problem here. Okay? That's all. This is exactly what a coupling capacitor does. And that's why you will see very often people talk about extremely large coupling capacitors, because they wanted to be able to couple all frequencies so that the RC is very large compared to the time scale of variations for any input signal. In practice, or if you want to feel it physically, all that means is when you try to change the input here, if this is a large capacitor, it will just not have time to charge up. When you keep changing the input, that capacitor will just not have time to charge up to let a DC steady state be reached. It will just let the variations on one side appear on the other side. That's all it is. This is why we use a very large coupling capacitance to feed small AC signals into the circuit. This is really the reason behind it. This was my V out. Okay. You really understand this, the basics of it, in terms of this RC behavior. So very often you will see circuits like this where people will say, here, you have a capacitor. It will decouple the circuit, the biasing part of the circuit from the input small signal. But then if you have a time-varying input, as long as that capacitance C is large, the variations at the input will appear there. Now you talk about, once you do that, now you talk about modeling the small signal behavior of the circuit. No, it absolutely resists change in voltage. That's what the capacitor is doing.
So why did we say the voltage, the set change at the end?
The capacitor resists change in the voltage across the two plates, right? So one side will follow the other. The capacitor does not change does not resist the change in one node voltage. It resists the change in the voltage difference. So if the difference doesn't change, means, yeah, absolutely, that's exactly what it is. It resists the change across in its own voltage, right, which is the drop between the two sides. That's exactly correct. That's a very good question. Why would I need the capacitor? Why not just connect it like that?
It essentially mimics it?
Are these two the same? Instead of a capacitor, connect a wire there. That's a very good question. Why not do this? The answer is it ruins my biasing, right? Because now if I want to calculate the bias point, the DC operation point, now this little V in also has a say in it. So imagine this little V in is some small variation around 0, right? Then you're essentially grounding this node, right? The reason you have that coupling capacitor is to decouple the DC and the AC problems and then couple the small AC back into the circuit after you've solved the DC, so that the DC part does not depend. Yeah. So consider this. Let's put some numbers to it, right? Assume this is 20 volts, right? And you solve this circuit. You find a bias point depending on these resistors. Your base bias could be at, let's say, 8 volts, right? Think about some example we did last week, right? Something like that. This capacitor in DC has no effect, right? And imagine that this V in is some very small sinusoidal 1 millivolt changing with time. Let's say 1 millivolt cosine of omega t. Okay? That's a small time varying 1 millivolt signal. All right? Now, if instead of this, if I do this, the voltage at this node is basically 1 millivolt around 0, right? At base. I'm directly imposing that. It's no longer what it would be if I had disconnected this part of the circuit using this capacitor. Does that make sense? Have to get used to it. What it really means in reality is that you, again, go back to here. You first solve the circuit in DC, find the operation point, the bias point, and then you add a small signal Vin on top of that. And this is how you do it in practice. Now I want to talk about modeling the transistor for only that small signal behavior. On the same circuit. What I'm really saying is that this circuit that we have here in DC, or to find the bias, looks like this. The capacitor has no role, or that part of the circuit has no role, because in DC the capacitor is an open circuit. And in fact, now you're talking about just the bias point. So you have the capital V. In DC acts as an open circuit. In AC now, once you have found the bias point, you want to look at the small signal AC behavior. If the capacitor is large enough, like we discussed, it practically acts as a short circuit for that AC signal. So I want to draw the circuit for that little AC small signal. And the capacitor will just act as a short circuit for that, because, like we discussed here, whatever change the input creates here will be transferred to that base. Now I'm interested only in the small signal, so I'll use small v and small subscripts. And this is what you have. By the way, what is the small signal component of the supply voltage VCC? What is the small signal component of that? 0. In small signal, this is as if you have grounded it. But to be entirely correct now, we have to be careful what we put here. Because in here, we have to include the small signal model of the transistor. You see, this is what we need there. The small signal model of the transistor. And that's what I want to talk about. What do we expect the small signal model of the transistor to look like? Think about that thing we came up with last time, that transconductance, GM. What was GM? What is the definition of transconductance? Does anyone remember from last time? You can look at your notes. It would be useful to refresh your memory. What is the definition of transconductance? Well, it's a conductance, so it's some current divided by some voltage. But it's not the conductance of one element. It's transconductance. It's the output current divided by the input voltage of the transistor. But it was a small signal transconductance. It was, in fact, the small signal output current divided by the small signal input voltage. Was small changes in the collector current divided by small changes in the base emitter voltage. This is from last time. The transconductance, these are both small signal. That's why I have small I, small c, and small v, small be. What we saw last time was that, and we talked about at the beginning of today, was that in small signal, you are approximating the behavior of the device with a linear behavior. And you're saying the ratio of the output to input is basically a constant, as long as both input and output are small. Can you guys draw a 3-terminal element that has this property, that the ratio of the output current to the input voltage is some GM? What would the model for that be? So we have 3 terminals. In small signal, I'll use small letters, B, C, and E. And I'm saying the collector current, the small signal component of it, is just proportional to the input voltage. If this is VBE, the collector current is just a multiple of that. That's all. So very similar to the large signal behavior or large signal model. Look, we had the collector current here depending on the input or base emitter voltage. But this was the full description. This was the full exponential dependence. In small signal, that exponential dependence has been replaced by a linear dependence, just a proportionality, GM times VB rather than exponential of VB, because you're looking at a small section of the curve. So you're approximating the exponential with a line. That's all. Now, there's, of course, the question of whether this is open. And the answer is not. It's not. There is actually some resistance also to be put there, some small signal resistance. And this resistance is basically the input resistance that you see from the base. This R is another parameter, is this VBE divided by the base current. The input resistance seen from the base. And that is the ratio of small changes in the base emitter voltage divided by small changes in the base emitter current, which again you can find in a similar manner to GM because you have the equations, right? This base emitter current is just the current of that diode, right? It has that exponential form. You can take dVBE by this current, and you get that. You can find it exactly in the same manner as we found for GM. Now remember that these parameters, these small signal parameters, depend on the bias point. We saw last time that GM was the bias value of current was capital I, capital C, divided by VT. But once you calculate them, you can now put that model here. And now you have a very simple circuit to solve, to find, for instance, V out. Because you can just replace what that dashed circle with what you have here. And so you have, there's no diode here. There is no nonlinearity anymore. The small signal behavior is basically a circuit with only linear elements, resistances, and transconductance. And then you can put this model in there and find V out over V in. small signal voltage gain. I'd like to close by making one other statement. Like I said in the beginning, all of the same approach applies if you're dealing with MOSFETs. It's just that the model for the transistor itself is a little different. The same approach, meaning separating the DC bias and then adding the small signal on top of that, applies when you have MOSFETs. But the transistor model is different because the output current is not exponential, but quadratic. With respect to the input voltage. For example, last time we saw that GM, let's remember that for your drain current, total drain current, in the active mode it was, or in the saturation mode, which is its active mode, was half it was this instead of exponential. And this led to a GM that was some proportionality here, but then had the bias point VGS minus VT. This is from last time. I'm just copying it. By the way, you might see this written sometimes, this thing, people might call it K. And this part might be called K prime. Just as a shortcut so that you don't have to carry W over L mu Cox. You will see this in people's notation. But that's it. Basically, you have here you have some proportionality. Okay. Now, next time we will do some examples of this so that you guys see how in practice this is applied. But I hope you can review this before next time. These are concepts that take time to kind of get used to. All right, thank you.